Welcome back to our course on introductory quantum mechanics for computational biologists. In the previous lectures, we have sort of introduced some concepts of classical mechanics from a different perspective. In particular, we went from Newtonian mechanics to the concept of energy, momentum, angular momentum conservation, and then all the way to redefine an equivalent approach to Newtonian mechanics, which goes under the name of Hamiltonian mechanics, or formulation of classical mechanics. And like we discussed several times over the last few lectures, the reason for taking the pain of doing this work is twofold. On the one hand, it helps us revisit some concepts of classical mechanics from a slightly different perspective. In particular, reversing the order in which concepts are introduced. To be more specific, in Newtonian mechanics, first comes the concept of force, whatever it is. And the concept of force is then used to derive work, therefore kinetic energy and potential energy, and therefore energy conservation. In the Hamiltonian mechanics, the hierarchy between these concepts is somewhat reversed. First comes the Hamiltonian that, for practical purposes, as far as our course is concerned, is basically an expression for the energy, mechanical energy. And from the expression for the energy, one derives equations of motion through the Hamilton's equations, and it does so in such a way that the resulting equation of motions are in fact consistent with Newton's equations. Basically, one derives Newton's equation out of the energy rather than the energy out of the Newton's equations. And in contemporary theoretical physics, the Hamiltonian is still the starting point of physical theory, while the Newton's equations are disappeared, right? They don't hold anymore. So basically, what we have done is to set up, and that was the second goal, to set up the stage for going beyond classical mechanics, because we identified there are three main logical steps, building blocks you have to work out if you want to devise a physical theory. First of all, we need to define what is a state I'm interested in. What is the object of my study? How do I define the state of a physical system? And in classical mechanics, the state of a physical system is identified as a point in phase space. Why is it so? Because only if I have a complete knowledge about the state in physical system at some time t, I can predict the state of a physical system in the future. So the goal of classical mechanics is being able to predict the state at some time t. So let's say the state of a physical system at some time t is the collection of all momentum coordinates and position coordinates. Remember, the capital letters are used to denote all collections of momentum and positions. So just to be specific. And similarly, Q is Q1. And the goal of any theory is, given the complete knowledge of a state of some initial time, find out what the state is at some time t, just typically later at T0. And in order to do that, we need an equation of motion. So that's the goal. And the equation of motion is basically something that tells me the time derivative of the state is equal to something else here. And whatever is on the right-hand side and whatever is your definition of state defines your physical theory. So in particular, for classical mechanics, whatever is here, the right-hand side of these equations is derived from the Hamiltonian through the so-called Hamilton's equations. As we shall see in a couple of weeks or maybe more, in quantum mechanics, you define the state differently for a reason that will become clear in a couple of lectures. It is untenable to define a state in terms of position and momentum of a particle because of the intrinsic impossibility of getting this knowledge in nature within a microscopic system. This is called the uncertainty principle. So because of this uncertainty principle, which we will discuss in great detail in the future, this cannot be our definition of state. There will be a new concept, new mathematical representation, a new definition of a state. Yet, it will still be true that the time that our goal will be the evolution of this new concept of state, which is called the quantum state. So our main equation that will enable us to compute such an evolution will be still in the form time derivative of my state equals to something else. And again, like in classical mechanics, this something else will be a function or defined once you define the Hamiltonian. So it really seems that the Hamiltonian is the heart of any physical system. Let it be classical or quantum. Just the way you use this concept and the way you relate it to the states and the state that you use to represent the physical systems are different in different theories. Okay, so before we move on towards discussing what goes wrong with classical mechanics as you approach the microscopic systems, which will be the topic of the next subset of lectures of this course, I think it's appropriate. I think it's quite appropriate to spend some time and make one example of how to use classical mechanics within the Hamilton's formalism to evolve a classical state, and what can you get out. So this is a very familiar example in classical mechanics. You most likely have seen it in a different language. Nevertheless, it's important for two reasons to discuss it. The first reason is that we will discuss the same problem in quantum mechanics later on in the course. And this particular model has a lot of applications. So it's good to have the classical mechanics example as a reference. And also because the second reason is because the same mathematics that we shall use in this problem will turn out in different problems during the course. So it's a good moment to stop and do some math work and get some practice and exercise and solving. So what I suggest to students to do as we go through this problem is to stop the video of the lecture and try to do things yourself before you see what I do to solve the problems. See if you can do it yourself. Remember, physics is all about being able to do stuff, not just look at other people doing stuff. If you cannot do stuff, if you you cannot figure it out yourself, you don't understand it. That's a sad but true law of physics that Feynman very nicely phrased in one of his famous books. I think it was Surely You're Joking, Mr. Feynman. He went around describing this philosophy he had in science, that if he cannot reproduce it himself, then he hasn't understood it. So, I encourage you to do things yourself and then look how I do it. So let's look at this problem. This problem is the harmonic oscillator problem, prototypical problem in physics. Now, this problem is so prototypical in science, in physics, that I dare to say that if we weren't able to solve this problem, basically in all the theories we've developed, from classical mechanics to statistical mechanics to quantum mechanics to relativistic quantum mechanics, if hadn't we be able to solve this problem in great detail, there probably would be very little or no theoretical physics at all. Because most of theoretical physics is based on starting from this model in many ways or other, and then elaborating more complicated generalizations. So really, this is a key problem, key prototypical problem in theoretical physics. And what the problem is all about? Well, in the simplest possible setting, which we are interested in this class. So that's 1D. The problem is find the equation motion of a particle in one dimension. So the state of the system would be my momentum and position of the particle. And the Hamiltonian would be the kinetic energy of the particle plus a potential energy, which I will represent this way. So this is the Hamiltonian, and we can formulate the problem simply as find the time evolution of this state. So in other words, given the system that time t0 is in position q0 and has momentum p0, find out what the position and momentum will be at some later time. That's the problem. Well, I deliberately started with a mathematical formulation rather than a physical formulation of the problem. We're not interested in the specific realization of this problem, but it's important nonetheless to try to understand what kind of problems we're looking at. So remember, in the Hamiltonian formalism, the first term is interpreted as a kinetic energy. And we already discussed that the second term is in fact the potential energy. So if you want to understand what physical system is this, let's derive the force, which is the negative of the gradient of the second term, which in this case is simply the negative of the first derivative, since this is a one-dimensional problem. So the force depends on position, and it's basically Q. So if I call this K, I discover that this is a linear force in the displacement, which already should ring a bell to most of you who had a physics education and say, okay, this is actually in fact a good theory to describe a point particle with a spring characterized by vanishing of negligible rest length and an elongation Q. So the problem is really, given a spring which has vanishing rest length, maybe, of course, it will be finite rest length, but we can neglect it over the scale of the elongation. So the elongation is always much larger than the rest length. Given an initial elongation and maybe an initial velocity, or maybe I throw my particle in one of the two directions, then find out how the system will swing back and forth. Where will it be at some time t? Okay, So that's the physical interpretation of the problem. So, okay, that's my Hamiltonian. So we know now how to go around with this problem. First step, we need to find or work out the equations of motions. And to do that, we simply apply Hamilton's equations. So let's be pedantic and do it step by step. Remember, Hamilton's equations are Q dot and P dot, because P and Q form my state, right? So if I want to get the gamma naught, I need to take Q dot and P dot. Now, I've been a little bit sloppy. Sometimes I've used a definition of gamma in which I put first the P's and then the Q's, and other times I use a different definition of gamma where I put first the Q's and then the P's. Apologize for this inconsistency in my notation. I am confident, nevertheless, that the real meaning is quite clear. It doesn't matter how you organize your P's and Q's into gamma as long as you stick to one or the other definition. So in particular, if I want to say that this is gamma, well, I could say like, if I give it this particular order, then my gamma would be the Q's and the P's. But because I see the Q's are on the first row and the P's are on the second row. But it really doesn't matter at all. So remember, Hamilton's equation says, in order to get a Q dot, you need to take the partial derivative of the Hamiltonian with respect to the P. And in order to get the P dot, you have to take the negative of the Hamiltonians with respect to the Q. So there's a nice symmetric formulations of the equations of motion. Now, physicists are nuts when it comes to symmetry. And the reason is that although we are supposed to be, so to say, unjudgmental and cold observers of nature, whenever we see symmetry, we see things that have similar order, we are under the spell of symmetry. We fall under the spell of symmetry. We have the impression that we are on the right track. I mean, most of the time it has been proven right, actually. So there's some aesthetic principle in science that traces back to the very time of Copernicus and Galileo. And I think it's a good point to stop for a moment to think about this. I like to tell stories always when it comes to symmetry in physics. And it's the story of Galileo's trial. So remember, Galileo was in trial against the Vatican, essentially, because he supported Copernicus' view, which put the sun in the center of the universe, of the solar system, which was identified with the universe at the time. Well, of course, the church was much more keen of the Ptolemaic system where the Earth was in the middle. And the trial was quite interesting. If you read the story of the trial, there's a very interesting passage because the people from, Inquisition, the church, they weren't completely dumb. Some of them were actually pretty educated and smart people. In particular, the Bellamino cardinal, who was in charge of the accusation, was no fool. And he made the following argument to Galileo. He says, okay, you, Galileo, say that we should not use Bible as a source of knowledge. We should use experiment as a source of knowledge. So that, on the Bible, it's written there, if you follow logically the implication of the Bible, the earth should be in the middle. But you say, no, experiment should prove the truth of a theory, not faith. But, you know, the Ptolemaic system, by the time of the trial, was extremely well developed. In order to make account of the data that people had observed for thousands of years, they had made it so complicated with micro-orbits over micro-orbits, it's called epicyclar and deference. There are like very complicated system that nevertheless, since it depended, so we could say today that it was like a function with thousands of parameters, all fitted to reproduce the data. And we all know that if you put 10 parameters on a curve and you use it to fit the data, you reproduce any theory. Right. So the Ptolemaic system was extremely well predicted. So the Cardinal Bellamino asked the question, why should I give up a theory that predicts the data even better than the Copernican system? Because the Copernican system is far from being exact because, it neglects, for instance, all the influence of of the planets with each other, if you want to compute the orbits, and of course, neglects also the influence of other, celestial bodies in the sky. So the agreement with the experiment was good, but not just as good as the Ptolemaic system, because the Ptolemaic system basically fitted a very complicated function with all parameters. So Bellamino made the question, if my theory predicts the theory better than yours, why would you believe yours? And Galileo says, it's so much simpler. The Copernicus theory is so much simpler. It's so symmetric. It's just the least you can possibly, think it, and it's so elegant, it cannot be wrong. And then Bellamino says, you see, you're using a metaphysical piece of knowledge, a metaphysical ingredient in your statement, which is aesthetics, and I use another metaphysical ingredient, which is Bible. So why should I give out the Bible for aesthetics? I mean, I'm not using exactly the words. I'm rephrasing. I'm taking the chance of this discussion to make it a little bit, tilt it a little bit to adapt it to the lecture. But I think it gets the point right here. Symmetry and aesthetics, elegance, simplicity, for scientists, for theoretical physics, has been used as a guiding principle since the very beginning, to the point that the famous Occam's razors approach that says if you have two alternative explanations for the same physical process and one makes the least assumptions and the least complicated, you should go for the very least theory, right? The very simplest theory is the one you should be preferring. I'm digressing this because it's important. We are making science, but we are humans. And humans see things with humans' eyes. And when they see something that molds into nice building blocks that repeat themselves according to some order, like you see in this case, then people are more keen to believe that the theory might have a content rate. Sometimes this has been proven to be dramatically misleading. And, thousands and thousands of millions of euros have been spent looking for supersymmetry, which was a theory for high energy physics discovered, invented for sake of aesthetics, essentially, to fit things in order based on things that would make things so much nice and symmetric. Unfortunately, no one has to date ever seen any sign of it, in spite of the incredible efforts done at LHC, at CERN. Look for it. So sometimes you get right, sometimes you get wrong, and we have always to be careful in using aesthetics and being aware that we are doing this. So this, of course, had nothing to do specifically with the problem of the harmonic oscillator, but I took the chance, and I always do in my course, to remind myself and my students about the role of aesthetical principles in science. Okay, now let's be more down to earth and complete this calculation. Well, this is clearly P over M, because only the kinetic energy contributes to this partial derivative. And this is clearly negative of d by dq of the potential Now, the first line tells me that the P and the Q are not independent variables, that the Q dot, the P's are essentially mass times velocity, which means that the P's are in fact momenta. And the second line tells that the evolution of momenta basically obeys Newton's equation, because if I substitute the first equation into the second equation, I get one equation, which is mq double dot equals negative u prime of q. We're using this notation. I'm using two new pieces of notation, which I already have discussed previously in this course. The dot notation is to denote time derivative. So double dot means second derivative with respect to time. And the prime denotes derivative with respect to the argument, in this case, to respect to coordinates. Now, since we are on one dimension, I don't need here to use partial derivative whatsoever. So if I do that, then I can rewrite explicitly now my equation in the following way. Now, now you begin to see why I chose not to use the notation kappa, but only the notation, but already explicitly pull out the factor m from kappa. And the reason is that there was going to be a cancellation with a factor of m here. So in the end of the day, the equation of motion need to solve is the following second order differential equation for the position. So what does this mean? I need to find one function. So my goal, my task, if you want, find a function q of t such that if I take second derivative with respect to time of this function, will give me a constant with a negative sign n itself. And this constant has to be omega squared. So basically, if I can find a function such that if you differentiate it twice with respect to time, you get itself up to a constant, then you have a function that satisfies the equation of motion. But of course, then you have to take into account also the fact that we know the initial condition, because this function can be probably too general for representing a physical problem, a specific physical system in which you start from a position and have initial momentum. So we will have to introduce the knowledge of the initial condition into this, as we see in a moment. But before we go into doing this math, and I'm going to go very slowly and very pedantic, because I think it's important to solve one problem all thoroughly to make sure we're all on the same paces when it comes to math. So let's try, there are methods to solve equations, but let's differential equation. So first of all, let's acknowledge this is a second order differential equation. So let's find out how to solve this second order equation. So basically what we are saying that doing two derivatives basically does nothing to my function. It only produces an overall constant. The function is almost blind to derivative. Well, it's tempting. So let's make some try. Let's make some attempts. It's tempting to, go back in our notes of high school and say, I remember there was a function that was left unchanged by time derivatives. And that was the exponential function, right? exponential function has this nice property that, you know, d by dx of e to the x was actually e to the x. I think we all remember that. And therefore, we might say, fine, now I put like omega square here, omega naught here, and time. So remember, now we want to find time derivative. So maybe our first attempt would be, I take the time derivative, and maybe I do negative omega naught time. If I take my first derivative, this will give me negative omega naught times exponent of negative omega naught in time. So if I now take an extra derivative, it means that I need to take one more derivative here. Well, you see what happens. I get almost what I want. I get an omega squared. I get the function itself as I would like to. Unfortunately, though, I don't get a minus sign. I get a plus sign. But if I go back and look here, I get a negative omega naught squared. So we are almost there in terms of, we are almost there, but not quite yet. And the reason is that when we pull down this prefactor twice, I get the wrong sign. And because when I do it twice, I cancel my -1 to -1. I get a -1 square, which is always 1. Now, I think this failed except, so this is failed. But sometimes failing teaches us something that guides us through the right path. And we will use these ideas of understanding our failure to correct the route towards the good solution over and over in this course. So the fact that we failed, but failed by going very close to the right solution, should guide us. So basically, we fail because we pulled down something square, and when we have this something square, we get a positive sign. We would like this something square to have the negative sign. But that's clear how things should go, because I know something that square gives me negative signs is the imaginary units I. So let's do a second attempt. Let's write a second attempt. And say, what if, as a function, I take something like a constant times, well, let's keep things as general as possible. Let's keep the plus or a minus here. Anyway, whatever sign that's going to be here, this sign is going to be killed when you pull it down square, right? So when I do the second derivative of this guy, I will get, well, let's forget about the pre-constant, which we don't care. When I take the second derivative of this function, with respect of time, regardless that I use plus or minus here the exponents, it doesn't really matter, because I get, if I was using plus, I get 1 times 1 is 1. But if I was using minus, I would get -1 times -1 is again 1. So regardless that I use plus or minus here, I get 1, I get I squared, omega squared, and then e to the plus minus I omega naught t. So from the purely mathematical point of view, we're there. Because this goes away, this gives me a -1 now. Aha! So now we solve the problem from a mathematical point of view. we have found a function whose second derivative, we actually found two functions with the plus over the minus of the exponent, such that the second derivative of the same function is proportional to omega naught squared to the function itself up to a negative sign. Okay, very good. Are we done? Yes, from the mathematical point of view. No, from the physical point of view, because this number here, this function, is not real valued, is actually complex valued. But when we measure the position of a particle, we use a real meter. We don't use a complex meter. Remember, the third requirement of a physical theory, beyond having a definition of state and an equation of motion, is being able to make predictions that are measurable, and you cannot measure imaginary distances. Right? So it's clear that this mathematical function is not quite the answer. However, from your course in basic complex number theory, you know that there are specific combinations of e to the ix and e to the negative I that are always real valued, and they are sine and cosine. So here is two functions, cosine of omega t. Well, this is, as you know, sine of omega t. Now I'm going to embarrass myself because I can never remember the correct ordering. I think this is the correct. There could be a negative sign in the exponent. Let me see if I'm right. I think I'm right. I might be right. Yes. And cosine, on the other hand, let me write it downstairs. Is plus with a 2 downstairs. Now, this means that although these two functions independently cannot work as a physical solutions because they are complex valued, if instead of them I use specific linear combination of this function, just sine and cosine, that I'm all set because these are real valued. These are real valued. So, in conclusion, I could say that if I take as a function of QT any linear combination of sine of omega naught t plus cosine of omega naught t, where a and b are two, any number, any real number, then I'm guaranteed that if I take the second derivative with respect to time of this function, I will get a omega naught squared cosine omega naught t, sorry, sine, plus b omega naught squared cosine omega naught t, and an overall negative sign. Now, I could have come to this conclusion without invoking complex numbers and exponent. The reason I chose to go through that tour was, first of all, to practice a little bit complex numbers and see how they can be useful to solve differential equations. And also to provide a logic that will be used later, because we will use exponents of complex phases, exponents of imaginary arguments to define quantum states over and over and over in this course. So it's good to have a first exposure to the use of function e to the I something. And to understand that those functions, e to the I something time, for instance, they are related to oscillatory behaviors, sines and cosines. There's this nice connection between complex phases and oscillations. You've seen all that in the mathematical premise course. I could have simply said, oh, remember the sine, when you differentiate the sine, you get cosine. When you differentiate the cosine, you get a negative sign. So if you differentiate it twice, the sine, you get a negative sign. If you differentiate the cosine, you get a sine, minus sine. And if you get to differentiate again, you get still minus cosine. So if you differentiate twice the cosine, you get negative cosine. That was enough for this discussion. So you don't need to go through exponents, but you will need exponents so much in this course that we might as well use them. Now, A and B are whatever function they are. You see, no matter how I choose A and B, the equation of motion is always satisfied. However, of course, if I change A and B, the position at some any time changes, right? Because for instance, if I set A equal to 0, then say the position at time equal naught is B. But if I change A not equal to 0, say, the position of time naught is not going to be just, oh sorry, that's always true. Actually. Well, what I was going to say, if I choose B equal to 0, the position at equal to 0 at initial time is always 0. But if I choose another value, for instance, B equal 1, the position at t equal naught is actually 1. So you see, depending on you, and the same happens if you change A, right? If you change A. So depending on how you choose A and B, you get different functions, you get different predictions. So what A and what B should I choose? So how to choose A and B? And that's where you actually, that's where you use the fact that in order to predict the position of a state at some time, you need to know the complete knowledge of the state at some previous time. Remember, our goal was always, from the very beginning, denoted as follows. Given the state at some initial time, compute the state at some final time. But given this, then the goal was set to compute this. So in other words, you've got to know how was the system at some time if you want to predict what the system would be in the future. For instance, so let's apply this. And let's be completely general. Let's be completely general. What do I mean? Well, let's suppose that at some time t naught, my initial position was q naught, and my initial momentum was p naught. When q naught and p naught are arbitrary parameters, it could be in the origin and still in rest, or it could be with a finite elongation and rest, or finite elongation and some momentum towards the center of the spring or towards the outward direction, whatever, making no restrictions. Well, how do we use this fact? This is extra knowledge, right? And we need that knowledge if we want to solve the problem of predicting the future of the particle. we need extra knowledge of what is called the initial condition. So, okay, given the knowledge of an initial condition, then we can get, maybe we can hope to use these two pieces of information. These are two equations. We have two unknown parameters, and therefore there is room for fixing A and B given this extra knowledge we're providing. So let's do that. Okay, so let's suppose the initial time, for sake of simplicity, we set the clock at the initial time. Doesn't matter how we set the clock as long as we keep track of it. So the simplest choice is to restart at the initial time by clock. Why is it simple? Because then simply I can kill the sign, because sine of naught is naught and the cosine of naught is 1. I can be more general and write here sine of omega naught t minus t naught and keep track that this can be anything. Why complicated our life? Lives are already complicated enough if we take the simplest possible configuration. So let's suppose we start the clock at the initial time. Okay, so at the initial time, this is q of time naught. And I'm copying this expression here, star, at the initial time. This is 0. The sine of 0 is 0, so the first term doesn't contribute, and the cosine of 0 is 1. So I get B. Oh, great. So rather than writing B, I can write Q naught, right? Because I know that at the initial time the system is at Q naught. That's my known initial condition. The extra piece of knowledge I assume to have. So here, I will not write B, I will write Q naught. Okay, let's get some information about, let's try to use the second initial condition. And the second initial condition is about the initial value of P, the momentum, right? But the momentum is in fact proportional to the velocity. So it's quite natural that if I want to use the information of momentum, I better take a derivative to compute the velocity and then set it equal to the initial momentum divided by the mass. So let's take the time derivative of this q of t. That's going to be omega naught a sine omega t negative q dot omega naught. Sorry, of course there's cosine here. And sine omega naught t. And then let's take this t naught equal naught. So I get the time derivative at t naught equals 0. And let me multiply by the mass so that I can get the P naught. I'm using the fact that the first Hamiltonian equation tells me the momentum is the velocity divided by mass. So this left-hand side is just P naught. And all I have to do now is to compute the right-hand side at the initial time T naught. Now is the second term that doesn't contribute. And I get omega naught A, and the cosine of naught is just 1. So all I get is that A is in fact the mass times P naught divided by the frequency. So I can finally replace this in here, mass P naught. Oh, of course I have a mass term here. So it's P naught divided this was wrong, is P naught divided by mass and frequency. Okay, I guess it's right. This is, of course, P naught. Okay, so finally, I was able to find a unique solution so that if I know the initial position and velocity or momentum, then I know the position at any time. And of course, I also know the momentum at any time by taking the time derivative and multiplying with a mass. So time derivative will be P naught divided by omega naught cosine, and that would be an omega naught pumping up. So it's going to be P naught cosine omega naught t negative Q naught omega naught cosine of t times mass. Okay, so finally, we know the state at time t, given the state at time 0. The state of time t is P naught omega naught m sine of omega naught t minus Q naught cosine omega naught t, and then P naught cosine omega naught t negative Q naught omega naught mass cosine. There's a mistake, of course. I very often do mistake, as you begin to realize. Likely, that's a sign. Okay. Now you should ask, well, fine, we have found two functions, linear combinations of two functions that do the job. Second derivative of this linear combination is returning same initial function up to a negative constant. But who tells me that this is so that I'm done, that maybe there are more functions which have this properties of giving, to more functions, such as if you take linear combination of this and other function, if you take the second derivative, you get the same function with a negative 5. So is this solution unique? Is this the unique solution? Oh, let me write the questions in a different page. Two questions emerge. Question number one, is there a unique solution? Second, is there always a solution? Now, maybe we've been lucky. Maybe this time we were able to solve this problem. Maybe some problems don't have a solution, not even numerical. Or maybe the real solution is more general than the one we have, and we only look at the partial solution, and maybe this partial solution alone is not able to describe all physical systems of interest, and we get the impression of having a right answer, but we just have a partial answer and ultimately get lost and never be able to reproduce nature. Well, both questions are positively answered by one theorem, which of course I will not derive. Physicists and mathematicians in their educations, they go through this theorem during the second year training or first year of training, depending on how they organize the teaching, and it's called the Cauchy theorem. And what does the Cauchy theorem says is that if you have nth order initial condition, nth order differential equation. A differential equation of nth order means that you have at most the nth derivative. So Newton's equations are second order differential equation. Acceleration is second order. So in our case, if you have a second order differential equation and you have two initial conditions, then there is always a solution and it's unique. This means that I have, as long as I find two functions and a general linear combination of two functions, then using two initial conditions, I can always find the constants, and I have always a unique solution to my problem. So if you have as many initial conditions, as many as information about the initial condition as derivative, you can always do what we did today. What does that mean in practice for us? We can visualize this in phase space. It's quite useful, actually. So let me draw the phase space. Remember, I put the P here, sorry, the Q downstairs, and the P here. So initially, I'm in a point in phase space gamma, which have a Q naught and P naught. That's my gamma naught. Now, given this, my system will evolve in time in one direction or another, and drawing an arrow here could be going the opposite direction. And we'll end up in some other state, gamma, at some later time. Now, what Cauchy's theorem says is that if you specify this point, you have only one orbit that takes you somewhere else. You never have multiple orbits. So this situation is never encountered, which, if you think about it, can be rephrased by saying the orbits in phase space never cross. The orbits never cross. Because if they did cross, then you would have multiple solutions starting from the crossing point. This very result has a tremendous implication for mechanics. It says that if, on the other hand, I do know the initial condition, and I know it exactly, I know all the information about the initial condition, then I can always predict with infinite accuracy the future position and momentum. So given the initial state, I can always predict the final state, and the final state means I can always predict the final position and momentum. So let's look at this principle of being able to determine with infinite accuracy, with arbitrary accuracy, given arbitrary accuracy on the initial configuration, the final configuration, the final position and momentum of the system is called determinism. Classical mechanics is in principle deterministic. In practice, it's another story, because maybe you don't have complete information about the initial condition. Maybe make some error in the initial condition, which will propagate into an error on the final condition. Now, some systems are such that if you make a small error on the initial condition, you will get a final position that is exponentially far from the one you would have gotten with a different initial condition. So if you perturb, if you get initial condition, let me draw it. And you get to some point t. If you slightly perturb the initial condition, down here, maybe because there was an error and you thought this was your configuration, but the real configuration of the system was this, then maybe at the beginning the trajectories are close, but on a exponentially short time, as you go on with time, they diverge exponentially. And the systems that behave like that are called chaotic. And the exponent that tells you how far you go there is called the Lyapunov exponent. I'm not going to go into that. It's not material for this course. But this is precisely the reason why you can never trust forecasts, weather forecasts, beyond just a few days, because all the data, no matter how accurate they are, they provide the initial condition of your clouds and pressure and dynamical systems equation after an error. And the error enables you to retain some predictive power only for a limited amount of time, but if you wait long enough, time will detach and the solutions will be completely uncorrelated. You make an arbitrary large error. So that's why no matter how your favorite weather forecasting websites tell you, you should never trust weather forecast beyond just a couple of days, three days. Because really, it's impossible to make prediction. Then obviously, if you're in August, it's more likely that there's going to be sun than rain, but that's because that's the chances of good weather in summer are good and in winter are bad, but that's not a prediction, it's more like a statistical inference based on records. Okay, so how does this diagram look for the harmonic oscillator? Is the harmonic oscillator a chaotic system? That's an interesting question. Now, if you look at what we found for the harmonic oscillator, it is a combination of sine and cosine. I don't have in hand the solution, which I worked out as I was doing that. I think if you go back a couple of minutes in this lecture, you'll find it should be something like P naught, if I recall well, M omega naught, then cosine, omega naught T negative. No, that's sine. I guess that was the solution if I'm. Yeah, I think. Well, you have the right expression. If this is not correct, please double check it. Now, I think it's even, there's not even negative sign. It's positive. And here you have the equivalent for the momentum. Now, if you draw this in phase space, it's quite easy to convince yourself that what you get out is ellipses. So basically, what you get out is that start from a point here, you draw in an ellipsis that goes back and forth through the same point. How do I know it goes through the same point? Because I know the orbit of the harmonic oscillators are periodic. I stretch it and I pass through the same point because essentially of conservation of energy. If when I go back to the same position, I had a different kinetic energy, then clearly energy wouldn't be conserved because the potential energy is the same, the kinetic energy would be different. So because of energy conservation, I'm bound to return to the same position here and draw circles. So basically, depending on how you start, different initial condition, harmonic oscillators, orbits in phase space are just ellipses. So clearly, if I make a small error, and rather than being on this orbit, I'm on this orbit, I will follow a slightly different orbit, but I will never depart exponentially. I will pass periodically arbitrarily close to my initial. So clearly the harmonic oscillator is not a chaotic system. It's a very stable, predictive system. However, Many complex systems, basically all of complex systems, as soon as you get up to, say, a few degrees of freedom, they very rapidly become chaotic. So determinism is a principle in classical mechanics, which very often becomes only true in principle, but not in practice. However, the essential point, which will serve as a reference for the next lectures, future lectures in quantum mechanics, is that even though I can have chaotic behavior, I can push the accuracy of my theoretical calculation better, arbitrarily better and better, by specifying with better and better accuracy the initial condition. So in other words, if I know my P's and Q with a better instrument that allows me to reduce by 1 order of magnitude the error, then I can improve my prediction at time t. And I can keep on doing this forever. Anytime a new instrument will come in, which allows me to do better measurement, I will be able to predict my results with better accuracy forever. This is determinism, not the actual ability of predicting it as is with infinite accuracy, but the probability of indefinitely improving your accuracy by improving your knowledge of the initial condition. And this property will be badly violated in quantum mechanics. In fact, in quantum mechanics, there will come a time where you will discover that no matter what you do with your measurement of the initial condition, there is a hard wall below which you can never penetrate, and you can never be able to know with infinite accuracy the position of a particle at any time. But we'll come to that later. But important to understand the concept of determinism in classical mechanics to understand its violation in quantum mechanics. Okay, I think this lecture was an exercise, but also allowed us to introduce the concept of determinism, and we'll discuss in the future how this is broken in actually quantum mechanics. I think that's it for today, and thank you for your attention, and I'll see you hopefully soon on this course, provided I can stop this lecture.